Hello everyone, this is not some fancy physics simulation, but a simple position controller. Today we're going to implement a basic PD controller and land this rocket on the moon. Bit banana. Okay, this is the objective. We have our little rocket emoji here in the lower left corner and our moon perfectly centered on the screen. We want to automatically adjust the position of the rocket so it comes to rest at the moon's position. For that, we're going to implement a very simple controller. Let me first give you a quick tour on the setup that I've prepared. We have a very simple HTML page here. There's a div with stars as background, a moon and rocket emoji, some style sheets on top to make things look nice, and the main.js file where the logic happens. In here we get the sky, moon and rocket elements from the HTML. We obtain the width and height of the sky and position the moon at its center. We also get the width and height of the rocket and position the rocket on the lower left of the screen. Here I prepared a velocity and acceleration vector for the rocket, both set to 0 initially for both dimensions. Here we got a little pointer down event listener that gets the position of your finger touches and mouse clicks. This way we can move the moon around and see how the controller reacts to adjusted target positions. This is the animation loop. It gets the current timestamp so we can calculate the delta time to the last animation frame. With that delta time value we can update the position and the velocity proportionally. In the draw function we simply set a style transform property on the moon and the rocket to move them to the calculated positions. And this code is used to make the rocket always point towards its velocity vector. Okay, let's see if this is actually working. I'm gonna assign a little negative velocity on the y-axis for the rocket, and we hopefully see it lift off. Nice, we're space bananas now. Okay, now that we understand the basic setup and see that the animation is working, let's work on the actual controller. But how are we gonna do that? The easiest solution would be to accelerate based on the distance to the moon. If we're further away, we accelerate more. If we're closer, we accelerate less. That's the simple P controller, where P stands for proportional. We start by adding a function to update the acceleration on every animation frame. Let's put it down here. We now need to calculate the distance between the moon and the rocket. In control technology, this is usually called the arrow function. So let's go with the name arrow here. So we grab the position of the moon on the x-axis and subtract the position of the rocket on the x-axis. We do the same thing on the y-axis. And there is our arrow function. Now we're gonna multiply that with a factor and assign it to the rocket's acceleration. Again, both on the x and y-axis, we're gonna take the arrow values and now we're gonna multiply that with a coefficient. That's usually called Kp. P for proportional. Let's put it up here. So const Kp. We're gonna pick a rather small number here. Guess what? I've done this before. Oof, that was quite fast. Did you even see the rocket? Let's slow it down a bit. Yeah, we can at least see the rocket, but we still see that it's oscillating pretty hard. If we move the moon around, it gets even worse. Okay, let's take a step back. So clearly this approach isn't enough. And if you think about it, it makes perfect sense. because the rocket is even accelerating if we are very close to the moon already. Only after we overshoot the arrow gets negative and therefore the acceleration, so we slow down, but way too late. So we need some way to slow down the rocket even before it arrives at the moon. And that's where the D term of the controller comes in, the derivative. It acts like a brake by looking at the velocity and slowing us down in proportional fashion. So let's create a simple PD controller. For that we're going to extend the update acceleration function. Besides just using the arrow here, we're going to subtract something. So we're going to have another parameter here called KD, and we'll multiply that with the rocket's velocity. We do the same thing for the y-axis. And finally we introduce that KD parameter up here next to our other one. After our first experience, I'm gonna make that a bit bigger to brake a bit more. Let's see how that works. Yeah, looking nicer. We still got some overshoot, but at least it's settling at the moon somewhere. Let's see if that's working when we change the position of the moon. Yeah, looks good. Yeah, I think now it's time to tweak the parameters a bit more. Let's say we don't accelerate so hard. Let's restart this. Oh, that was accelerating even harder. Wrong direction, my bad. Let's try like this. That looks much more like a moon landing to me. We still have a little wobble here. Maybe we can dampen that even more. No, that's a bit too slow. Do it like this. That's pretty nice. Now that we implemented the controller, it's your turn to tweak those parameters for the smoothest moon landing or the biggest overshoot maneuvers. Let me know which controller parameters work best for you in the comments. I put a link to the code and a deployed example in the description. If you like this video and you want to support the channel, please consider subscribing. See you next time, BitBananas.